Hello and welcome, I'm your Code Monkey. Let's learn how to get started using Entity Dots. This is a technology stack that can provide some insane performance results, literally 100x faster in some cases, and thankfully learning the basics that is actually pretty simple. Here let's learn what is a component, what is a system, and what is an entity. Then we're going to learn how to create a job and run it with the burst compiler for some insane performance, and also of course see how to combine both entities and game objects and interact with them back and forth. This video actually turned out pretty long because there's so much to cover. There's timestamps throughout the video. I've been researching all documentation and working on this video for the past 2 weeks, so if you find the video helpful and you're feeling generous, go ahead and drop a super thanks on the video, or simply hit the subscribe and the like buttons. It's a small thing, but it really does help, so thanks. Also, huge thanks to Danny from the Entity Dots team, who helped me by answering tons of my Dots questions so this video could be as accurate as possible. Now over here on this video, this is going to be a technical tutorial on how to start using Dots, but if you're looking for a high-level overview on the theory behind what is Dots, what is ECS, and so on, for that, I highly recommend the video from the channel Turbo Makes Games. That one is a really excellent explainer of all of the components that make up Dots, as well as the pros and cons and when to use it and when not to use it. So go ahead and watch that video for the theory, and over here let's learn the technical part on how to actually use it. Although, let me also quickly remind you that you don't have to go full Dots or full game objects. The ideal workflow is to mix them both. So Dots is really just another tool in your toolbox. It is indeed a little bit more complex compared to game objects, as we're going to see in a little bit. It is an advanced tool after all, although it's honestly not really too complex once you understand the basics. And of course, that complexity actually buys a ton of excellent benefits. So even if you're working on a relatively simple game, I would still encourage you to watch this whole video to the end, just to be aware, just to remember that you have this tool at your disposal in case you need some excellent performance at some point in the future. You don't have to use it for everything, but for some cases it is an absolutely excellent tool. And also, just a question for my own purposes, I would love to do a complete Dots course in the next few months, so let me know in the comments if you would be interested in that, and specifically let me know what type of game you'd like to see made. Now, the obvious answers would be a factory game or an RTS, but could also be tower defense, third-person shooter, vampire survivors-like, something like that. There are plenty of genres where Dots makes a lot of sense, so do let me know your thoughts in the comments. I'm currently working on a complete C# course, and after that one, I plan to work on a Dots course. Or if you're watching this several months in the future, maybe I've already done it, so check the pinned comment. And if you use Unity at all, then check out my Ultimate Unity Overview course to learn how to make better games faster. It features over 70 lectures, each covering a different tool or feature of the engine, including many of which you might not know about and might be super useful for whatever project you're currently working on. Okay, so let's begin by making the most basic demo possible. Let's make just a simple cube rotating. Now before we do that, just some notes. In terms of Unity version, over here I'm using the Unity 22 LTS, although you can also use the 23 beta if you like, it should be pretty much the same. And if you're watching this many months or years in the future and using Unity 6, then it should still be mostly the same. Then Dots uses a lot of source code generation in order to simplify various things. So for that, you need to be using an IDE that supports that. In my case, I'm using Visual Studio 22, the free community version. And then they also recommend that you modify the domain reload setting. So for that, here in Unity, let's go into Edit and then Project Settings. Then on the left side, go into the Editor tab, and over here, let's scroll down. Find here the interplay mode settings, and let's enable these and make sure these two are unticked. Now importantly, you should know one side effect of this is that your static fields and events, those will not be reset by default. Meaning if you set some data on a static field, then you stop playing and start playing again, that data will persist. Whereas if you have domain reloading enabled, if so, it will always clear the data before starting. So just be aware of that side effect, just be aware of what this option does, and when working with Dots, be extra careful about any static fields or events. Alright, so here in the editor, let's begin by installing the package. So as usual, let's open up the package manager. Up here up top, let's go into the entity registry, and then over here, let's scroll down and find the entities package. Alternatively, if you don't see it, you can also install it by name, so com.unity.entities. You would basically go up here on the top left corner, add a package by name, and put in this name com.unity.entities. But as long as you are using a recent version, you should be able to see it, so let's just go ahead and install. Okay, it's done. Now the other one that we need in order to be able to render things is the entities graphics. You only need this one if you actually want to render entities, meaning you can use just entities without any entities visual. But over here in this demo, I will indeed be rendering some entities, so let's go ahead and install this one as well. Now, one more note related to this, entity graphics, this one only works with either URP or AGRP. It does not work with the built-in render pipeline. So here in my project, I have my project set up to use URP, the Universal Render Pipeline. And they also recommend that entities rendering be used with forward plus rendering. So let's go ahead and set that up. So let's go into the render pipeline asset, and inside, let's go inside the actual render object. And over here for rendering path, let's put it on forward plus. Okay, that should do it. Let's also make sure all the other packages related to Dots are also installed. Again, remember how dots is really not just one thing, it is actually composed of the entity component system, or ECS, that's the entities package that we just installed, but then it's also composed of the job system and burst. Those should both automatically be installed as dependencies. So if you look over here, burst, yep, this one should be installed. Then the other one is the mathematics library, yep, also installed. And finally, the collections library, yep, also installed. Okay, great, so we have all the packages that we need. Alright, now let's begin by making our first entity. And the way we do that is first we create a subscene. So over here on the hierarchy, click on the plus icon, and let's create a brand new subscene. Then give it some kind of name, so over here, entities subscene. Alright, there it is, here we have our subscene. Now this subscene, this is an ECS specific thing. Basically, any objects that we place inside of this subscene, all of those will automatically be converted into entities. So inside, for example, let's create a new game object, and let's go inside 3D and just make a basic cube. And yep, look how that one is indeed inside the entity subscene. And now this game object, this will automatically be converted into an entity. If we look on the inspector, and down here we can see something for the entity baking preview. You can click to expand this. And over here, basically we can see all of the components that won't be baked based on these regular components. Also, one very important thing, the system is smart enough to be optimized to only create entities when they are needed. So if we create a cube like this with these visual components, then it will indeed create an entity and add all of these components. However, if I go in the subscene and I create just an empty game object, if I do, yep, nothing shows up here because this one won't actually be baked. If the game object has no components, nothing at all, then it will not actually create an entity. So with the cube selected, another way that we can see the entity components is on the inspector. On the top right corner, we have the circle button. And if we click on it, we can basically toggle the inspector between various modes. Right now we are seeing the default mode, which shows the usual game object representation, so the usual components you're used to. And then if we click on runtime, yep, now here we can see the entity representation. So instead of the normal transform component, we have a local to world. Then we've got a bunch of things to handle rendering, render bounds, and so on. So basically these are all of the entity components that are created automatically by the baking system compared to the regular monobehavior components. By the way, here's one quick tip. Instead of over here constantly jumping back and forth between these two modes, we can basically leave this regular inspector as a regular game object inspector. And then we can right-click on the tab, and let's create a new tab, add a new inspector tab. And on this one, let's go ahead and swap it out into the entities. This way we have two inspectors, so we can very easily swap back and forth between the two representations. Now another place where we can see entities is on the entities hierarchy. So for that, let's go into Window, and go down into Entities and open up the hierarchy. And yep, in here we can see all of the various entities. Right now it still looks exactly the same as the regular hierarchy, but if we now hit on play, yep, here we see all of the entities that were automatically generated. And again, if I select the game object, the one that has no components, like I said, this one does not create an entity. So if you look in the inspector, yep, it says this one does not exist anymore. Because again, this one does not get baked because it is completely empty. Okay, so for now, let's get rid of the game object, and we can actually put the entities hierarchy next to the regular hierarchy. And for visual, just for fun, let's attach a different material, just to make it easy to see. So I'm going to go into the regular inspector, again, the regular game object inspector with the usual components that you're used to. And over here, I'm going to drag the material. And yep, and I can move it around. And again, note how all I'm doing is really just interacting with game objects, and then everything gets automatically converted into entities. Okay, so now that we have our entity, the next thing we want to create is a component. And the way we do that is with a script. So let's go ahead, right click on the project files, and let's create a new C# script. And for this one, let's call it rotate speed. Now, importantly, we do not attach it to anything, so just create the script and let's open it. And over here, first let's just get rid of the default functions. Okay, so now we need to do two things. First, we do not inherit from monobehavior. Instead, we are going to implement iComponentData. It's this one which exists inside the namespace unity.entities. So make sure to add the using, and yep, this is it. And secondly, this is not going to be a class. Instead, it is going to be a struct. Now, if you don't know the differences between those two, go check out my quick video on it. Basically, structs and classes, those are stored in different places in memory. And the way that dots is so insanely fast is really mostly all about memory management. So a lot of things in dots are used as structs. Usually that just involves replacing class with struct. But like I said, definitely go watch my video on that topic. If you're going to use dots, you absolutely must know the differences between those two. Otherwise, you will go crazy at some point in the future if you don't know how some things work as copies and some things work as references. Okay, so with this we have our component, and components are basically just containers for data. So over here we can place whatever that we want. For example, let's just add a public float and just call it value. This is going to be our rotation speed. Now, normally I always tell you not to make everything public. Normally I tell you to make fields private, and if you need to, you can make some functions to get and set that field. And technically over here on the component, you can add functions. That is allowed, but you really should not do that. Components should really only hold data and no logic. So for components, you can really just define a personal rule to always make them public since they only ever hold data. Kind of similar to the rule that I defined for myself when working with scriptable objects. I also use those only as data containers, and I also make those with public fields. Okay, so this is just our super basic component, just one piece of data. However, just like this, we still haven't attached it to our entity. If here in the editor we run our code, look in the entity inspector, and nope, we still don't have our custom component. And since this one is an iComponent data instead of a mono behavior, because of that, we can't simply just drag it. This does not work. So in order to attach components to entities, we have several ways of doing that. In order to use the exact same GameObject workflow that you're used to, for that we need to use the baking system. And the way we do that is actually super simple. We just need to make what is called an authoring component. So let's make a new C# script. And for this one, let's call it rotate speed authoring. Now here, technically you don't have to append authoring to the name. It's really just a nice convention to follow. So let's make this script and let's open it. And now this one is indeed going to be a regular mono behavior component. And over here we can add whatever fields we want. So let's add the exact same ones that we had in our component. So let's just add a public float for our field. Now over here in the editor, let's select the cube. Let's go into the regular GameObject inspector. And over here, let's just attach the component just like any other component. So let's attach it and put the field, let's say on 3. Okay, great. So basically now we have a simple component that just has our value field. And we have a simple authoring component that we then attach to our GameObject. What is left is really just our baker in order to turn one into the other one. Now the baker is going to be a class, and by convention we should put the baker class directly inside the authoring class. You don't have to, but it just helps to keep things organized. So let's make a private class, call it baker. Again, the name also doesn't matter, just a nice convention. And now what does matter is that we actually extend the baker class. This one takes a generic. If you don't know about generics, check out my quick video on them. And then we put in the type for our authoring class. So in this case, the rotate speed authoring. Okay, so this is what we do, and then in order to use this one is inside unity.entities. So let's make sure to do that. And now in order to do this, we need to implement this abstract class, which requires implementing this bake method. Okay, so we have this, and now here is where we basically convert the data from our authoring component into our actual ECS component. So we're going to use the function add component. Now importantly, this is the baker add component. This is not the regular GameObject add component. And for this one, first we require an entity reference. So for that, we can use the function getEntity. This one requires us to use a transform usage flags. This is an optimization thing. Basically, if you set it as none, then the entity will be converted with no entity transform component. So if you never need to move an entity or have a position in the world, then there's really no reason to include a transform component. But in this case, for our demo, we do want to transform. We want to rotate our cube. So for that, instead of none, let's go with dynamic. And this is going to return an entity reference. And then we can simply use this entity reference to add our component. And then for our component, we really just create the one that we just created. So the rotate speed component, and then we initialize it with our values. So in this case, the rotate speed value. Let's go inside the authoring component and grab the value. Okay, so yep, that's it. In summary, we have our rotate speed. This is a regular component, so iComponent data, just an ECS component. And inside we just have a value field, but this one cannot be attached to a game object. So for that, we create an authoring component. This one is a mono behavior, and this one we do attach to our object. We expose a field on this one. By convention, it should probably be the exact same name as the one on the component, but technically it doesn't have to be. So here in the editor, we added that mono behavior component and we assigned the value. Then we created a baker class that extends the baker entities class. And on this one, we need to override this function. And basically the ECS system will automatically run this function. It will pass in this reference for the authoring component. And then over here, we get the entity that the baker is currently being run on. And we call add component in order to add our custom component, and then we just manually assign the value to the exact same value. Okay, so with this, let's test. Alright, so here's our entity, let's select it, go into the entities inspector, and let's scroll down and see. And yep, here we have our rotate speed component, and yep, the value is indeed the one that we set. Alright, awesome. Now, just one more note on a possible optimization here. If you want, you can do it like this, so basically having two separate scripts, one for just the component and one for just the authoring component. Or alternatively, you can simplify this and just put everything on the same script. So over here on the rotate speed, I'm literally just going to copy this code and paste it directly inside of this file. Then over here on the editor, just delete the rotate speed script. So we just have one file, one script, and inside that we have both the component, the authoring, and the baker. So yep, everything still works exactly the same, except now it's all much more compact, all in just one script. Although one note on this method, which is that the file name the name for the actual file for the script, this one has to match the actual authoring component. It needs to match the script that we are using over here on the mono behavior. If we rename this file to something different, to just the file name of the actual component, if we did, it would not work because Unity expects the file name to match the mono behavior class name. So if you follow this method of putting everything inside one file, one script, then just make sure that file name actually matches the authoring mono behavior component. Okay, so we've already learned about entities and components. However, just like this, we're really just attaching some data to an entity. Nothing is moving, nothing is changing. So what we are missing is the S in ECS, which are the systems. Systems are what actually modifies the data in the components. So let's begin by making a brand new C# script. Call this the rotating cube system. And again, we don't attach it to anything. Let's just open it. And now here, again, same thing. We do not extend mono behavior. Instead, for a system, we have two possible ways of making them. One way is to make this a class and extend SystemBase inside Unity.entities. This is how you make a system that deals with managed types. So things like game objects, transforms, delegates, and so on. Also a note is this needs to be marked as a partial class. This comes back to what I mentioned in the beginning of how dots is very much based on source generation. Basically, we're marking this as partial, and then the dot system will write the rest of the code. So this is one way, making a system base. Like I said, this one is for managed data. And the other way is instead of making a class, we make it a struct. And instead of system base, we implement ISystem. So this one is meant for unmanaged types, so structs, ints, bools, and so on, which in turn means you can use burst on this one, making it much faster. Basically, by default, you should probably always try to make an ISystem unless you specifically need to use a managed type, in which case use a system base. However, also let me make sure one very important thing about systems in general. Both ISystem and system base, both of them run on the main thread. Just making something a system does not make it multi-thread. For that, we need to make a proper job, which I'm going to cover later on in the video. Okay, so here let's use an ISystem. So it needs to be partial, needs to be a struct, and needs to implement ISystem. Then over here on the ISystem, we can implement three functions. We can actually inspect the system definition. So let's go ahead, right-click, go to definition. And here we see what we can implement. So we can implement the onCreate function. This one happens when the system itself is created. We can implement onDestroy. So this one is called when this system is destroyed. Then of course we have the onUpdate, and this one runs on every update. So pretty much the same thing as the normal mono behavior update. So let's go ahead and implement our onUpdate method. So just go ahead, do this, our public void onUpdate. And now here we want the system to run and do something on some entities. Right now we really just want to rotate our cube. And the way that we do that is with a for each. And in this case, we want to find entities that have our rotate speed component. So we're going to find the rotate speed in, and then basically do a query for all of our components. So for that, we go inside the system API and we call query, and then we pass in the types that we're looking for. So in this case, rotate speed. Now, another really important part when working with ECS is being very clear with when we want to write or when you just want to read. And the way we do that is by either writing refrw or refrow. This is a class that uses generics once again, so don't be confused about the amount of angle brackets over here. Like I said, we have refrw, so this one is meant for read-write. But if we never need to modify anything, then we can use refro for read-only. This becomes really important later on when scheduling jobs, since you can have multiple jobs running concurrently if they're only reading the same data, but you can only ever write one job at a time. In this case, we really just want to read the rotate speed, so let's go with refro. And of course, over here for the parameter, instead of just rotate speed, we also have refro of type rotate speed. Although, let me also make one note. Technically, like we saw, if we erase the refro, technically this is valid code. We don't have any errors. Basically like this, it defaults to read-only. However, it's also using a copy instead of a pointer reference, which can cause some performance concerns. So even though this is technically valid code, you should always explicitly mention whether it's refrw or refro. Okay, so basically this will do a for each on all the entities that have our rotate speed component. But in order to rotate them, for that we also need the transform. So over here in our query, let's also include the local transform component. This one exists inside using unity.transforms. So we have this one, and for this one we do want to modify the transform in order to actually rotate the object. So for this one, let's go with refrw. And for our iterator variable, instead of having just one, put it inside parentheses, because over here we have basically a tuple, so the refrw for the local transform like this. By the way, one note here, you can write code like this, meaning define the types and the name for the variables, or alternatively you can also just use var, so just var and then just the names of the variables. So this is also perfectly valid code. Now, some people like this method. The official documentation uses this quite a lot, although personally I am not a fan of var. just because I like to be as explicit as possible. So personally, I really prefer to define the actual type, so just like this. But like I said, this is just personal preference, both ways work, so feel free to use the var method if you prefer that one. Okay, so here now we have both of our components, and this for each, the code in here, this will cycle through all of the entities that have both of these components. Now here we can just apply a rotation. So in order to rotate, let's go inside the local transform, and then first we need to access the underlying component with either read or write. In this case we do want to write, so let's access the value rw. And then on the local transform, we can call the function rotate_y to rotate on the y-axis. However, this function actually rotates a copy instead of modifying the original local transform. So we actually set the value rw equals whatever this function returns, and over here for the rotating angle. For this, let's grab the speed value from the component, so rotate speed. In this case, this is a read only, so let's grab the value ro, and then we grab the value, the one that we define inside the component. And finally, as always, when doing any movement or rotation, we want it to be frame rate independent. So over here, we need to modify by delta time. And inside the system, we get that through systemapi.time.delta_time. Now, important, it's this one when working with entities. It is supposed to be this one and not the usual time.delta_time. Basically, this has to do with the fact that you can have multiple worlds and multiple systems with different time frames. So when working inside of ECS, always use this one inside the system API. So with this, yep, this will indeed rotate it. Now, just one tiny thing, like I said over here, the rotate y, this one doesn't actually modify this value. So technically over here, we can just read in order to apply the rotation. So just make this one an RO, and then we actually assign it to the RW. Again, when working in DCS, it is important to be very clear about read and write access. And just like this, everything should be working. So basically this system, this will work on every single entity that has both a rotate speed and a local transform component. Then it will run this code on those entities, which in turn is going to rotate it on the y value based on the speed defined in the rotate speed. Okay, so let's test. And if right away we do see our entity rotating, and if I click to inspect the cube, yep, over there we can see the local transform is constantly modifying. And if we go down here, we can see the rotate speed. And of course, if we modify this, increase it or decrease it, and yep, it modifies the speed. All right, awesome. Now if we want, we can try making a bunch more cubes. By the way, when working with entity subscenes, you can also use just regular prefabs. So let's rename this to rotating cube. And I'm just going to drag it into my prefabs folder to make a regular prefab. So this is a normal game object prefab. I'm going to cover how to spawn entity prefabs later on in the video. Right now I'm just making this a cube just so we can duplicate and create a bunch of them. So let me create a whole bunch of them. And then later on, if we want to modify all of these, we can just modify the original prefab. Okay, so here we have a whole bunch of cubes. And if I hit on play, yep, all of them are rotating because again, the system works on all entities that match the query, no matter how many they are. Related to systems, we also have the systems window. So let's go into window and then over here into entities and systems. This window basically shows all the systems that are running, how long they are taking to execute, and how many entities they are being run on. So over here we can find our system. By default, it's going to be inside the simulation system group. And over here we do see our rotating cube system. And yep, this one is running on 7 entities and taking 0.01 milliseconds. Also, one note on systems is technically they can be created before the main scene is loaded. So generally, it is actually good practice to make sure they only run if the actual entities that you want, if those have already been spawned. So to do that, it's good practice over here to also implement the other function, the onCreate. And on this one, let's say we want to run the system only when there is at least one entity with our rotate speed component. So we do that by accessing the state. So this is this system state variable. And we call require for update, and then pass in the type that we want to require. So in this case, the rotate speed. Basically, this will make sure that this system, this update will only run once we have an entity that has this speed component. Now, technically, this isn't absolutely necessary. Like we saw, our code ran perfectly fine without it. That is simply because the query that we are doing here, this one was simply returning an empty list before any cubes were spawned. So if the list is empty, the for each is simply not going to run, so there's no problem. But for example, if we had other logic over here that somehow assumed that a cube already existed all the time, if so, you might get an error. Whereas by adding the require for update, this one makes sure the update function, this one only runs when there is at least one entity with this component. Okay, so far so good. Now, like I said a while ago, making something a system does not automatically make it multi-threaded. This is all still running just on the main thread. We can open the profiler and see. So over here, let's go into window, then analysis, and open up the profiler. And we can click on a frame and be able to see, let's expand this. Over here on my job, look at all my worker threads, and none of them are actually doing the rotate cubes code. Everything is still happening all the way up here if we find it on the main thread. It's really small, so it's really hard to see, but yep, here it is, the rotating cube system. This is all running still just over here on the main thread. Let me just add some dummy code just to slow this down so we can more easily see. Okay, so here I just wrote some dummy code just to waste some time on the CPU. So just a variable that I'm multiplying and dividing a ton of times and then using it over here in the calculation. Since I'm multiplying and dividing, the final result will be 1, so it won't affect the actual rotation speed. It should just take a bunch of time, so let's see. And yep, now we can much more easily see, yep, all the code is over here. Again, all of the worker threads, all of these are idle. All of our code is still running just on the main thread. Currently taking 7 milliseconds to run just a handful of cubes. Now, to get those massive performance boosts that Dots is famous for that we need to use the job system and burst. Which, just to clarify, those are not exclusive to entities. You can make your game entirely with game objects and you can still use the job system and burst. Those are not dependent on entities. So first, let's just enable burst, which is super simple. If you don't know, the burst compiler is really one of the best things about Dots. It is basically a magical button that makes your code run orders of magnitude faster. In order to enable burst, you just go up here onto the jobs menu under burst and just make sure to tick enable compilation. Which, by the way, right away, you might be asking, if burst is so good, why isn't it always enabled? Why is it a checkbox? And that's because when some error happens, it can be tricky to debug if burst is enabled, just because of how burst optimizes the low-level code. So while developing, if you find some errors, it might be useful to actually disable burst so you get some proper error messages. But when making a proper final build, definitely always make sure to enable it. Okay, so this one really just enables the burst compilation. It just enables the potential to use burst, but by itself it's really not doing anything just yet. For that we need to go to some functions, like over here on the onUpdate function. Let's say we want to use burst on this one. So for this we add an attribute to this function, and we add the attribute burst compile. So this one which exists inside using unity.burst. So this attribute like this. And yep, just like this code will be compiled with burst and will be insanely fast. There's no need to do anything else. Let's just test. And yep, right away it does work, so you can already see the difference. Previously our system was taking 7 milliseconds, whereas now, just by literally enabling burst, now it is taking literally 0.004 milliseconds. Now actually in this case, I think the compiler is way too smart and basically sees that what I'm doing here is nonsensical. So this code makes no sense, so I think the compiler is smart enough to pretty much just erase this. That is why it's such a drastic speed up in this test. But in pretty much every normal scenario, just enabling burst makes insane speedups. This is really insanely impressive for literally just one button click. And also one note, sometimes you might see some code that also has the burst compile applied over here into the system struct. If you want, you can add it, doesn't change anything. Basically the auto generation, the source code generation, that one is smart enough to know that if you use burst compile on any method, it automatically adds it. So technically you only need to add it on the methods. Now, while burst does indeed work pretty much like magic, it does have some limitations. The main one being that it only works on unmanaged types. So if you use a class inside this function, then you cannot make it burst compile. This is why ECS is very much based on structs and a data-oriented design. It's so you can benefit from these massive speedups, including using burst. And to make this truly insanely fast, that's where we use the next part of Dots, which is the job system. Again, right now, even though we are using burst, which made this insanely fast, even with that, it is still all running just over here on the main thread. In order to make it multi-threaded, that's where we use the job system. So first thing we do is we need to create a job. And for that, we make a struct, so let's put it right in here. Let's make a public struct, call it rotating cube job. If you want, you can make it in its own file, or really just over here right next to the system. This works great. So we do this, and now we implement one of the several IJob interfaces. There's a bunch of them depending on what exactly you're trying to do. If you're trying to run some non-entity code, then you should probably use the IJob4. Also, by the way, there is an IJob4 and an IJob parallel 4. However, you really should not use this one. This one is really only here for backwards compatibility reasons. Instead, if you need something not to do with entities, you should use IJob4. And then if you need to make this code parallelized, then you can simply call schedule parallel, which we're going to see in a little bit. But over here, we want to do some work on some entities. So for that, let's use the IJobEntity. Okay, so we do this one. And for this one, same thing, source generation. So this one also needs to be marked as partial. And then like it says here, we need to implement an execute method. So let's make public void execute. And over here for the parameters, for this one we basically add the components that we need, just like we did up here on the query. So we are going to need the local transform, and then we're also going to need the rotate speed. So we need these two components, and then again we have the same considerations we had previously with regards to read-write, except over here instead of using refrw and refro, instead of that, when we want something just read-only, instead of refro, we just add the in keyword. This makes it read-only, and when we want read-write, for that, we're going to add the ref keyword. So just like this, and then the code inside is going to be exactly the same, so I'm just going to copy paste that, except we now don't need to go into the value row, we just do just like this, so just erase these like this. And then over here, when working inside a job, we don't have direct access to the system API. So in order to get our delta time, let's pass it over here as a simple field in our job. So float for delta time. And then over here, we use this thing. Okay, so this is going to do pretty much the same thing. So basically, this job will be executed on every single entity that has both these two components, just like we had the query up here. It is going to execute that, and for every single one of those entities, it is going to run this code. So here we have defined our job. All that's left is to actually run our job. So for that, let's go up here onto our onUpdate. And right now, we are not going to use the system query method, so let's just comment this one out. So comment out the for each. Instead of doing that, we just create a new job. So new rotating cube job. And inside we need to pass in the delta time. So let's pass in the same thing, go inside the system API in order to grab time.delta time. This is going to return a rotating cube job. This simply creates a job. And then after creating the job, then we have two options. Number one is to call run. This one will make it run immediately on the main thread. So this one can be sometimes useful for debugging, but in most cases you probably don't want to use this one. Instead, you probably want to use schedule. This one will schedule the job to complete at some point in the future. It will be completed either by the main thread or any worker thread. It really depends on which one is busy. This one completes the entire job in just one thread. And then finally, we have the schedule in parallel. This one will basically split the job into multiple chunks and create multiple jobs that run on multiple threads all at the same time. So first, let's actually start with a simple one, just a regular schedule. So let's do this and test. Okay, so there it is, and the cubes are all spinning. And if we look, and up here we can see there we've got our job, and it's actually being handled over here by worker 1. Now, depending on what you're doing, it might complete in the same frame, or in this case, it might take 2 frames to complete. If you really want to force the job to complete, then over here on the schedule, you can pass in the optional state.dependency. Now, this one returns a job handle, and if you want to force it to complete, you can call complete. And basically then down here, you can write some code that assumes that this job has already been completed. However, you should really avoid this as much as possible. Instead, you should let the job system actually decide when to run jobs, and if you need some code to run after some job has completed, then you basically should just make that second job a dependency of the first job. So ideally, you never actually do this, you just call schedule and then wait for the job system to actually complete the job. Although one important note is how over here schedule, this is actually a shorthand, so the source generation then replaces this, so basically puts the state.dependency inside of here, and sets the new state.dependency equals to this. So when you call that shorthand, it is actually doing this. This basically ensures that as you schedule a job, it will have the correct dependencies. But I should also mention that while the shorthand works great if you're doing an IJobEntity, this code will have problems if you use an IJob4 because then it will not pass in the correct dependencies. So in doing anything other than an IJobEntity, then make sure you explicitly define the state.dependency as a dependency of that job instead of using just a shorthand. Okay, so like we saw the schedule, this one schedules on just one worker thread. So over here we have our job running on just this one. And the other one that we saw is the schedule in parallel. This one will run the job on multiple threads. However, this one actually has a really sneaky thing that confused me quite a lot while researching this video. This one supposedly splits this job across multiple worker threads. However, if we test this, and nope, everything still looks the same. It is still running on just one worker thread, and all the other ones, these are all idle. So this is the part that really confused me. It confused me why this one was still running on just one thread. I even made a post on the forums asking for some help, and thankfully I received some really excellent responses. The answer is that apparently this one splits across multiple threads, but it is based on chunks. So since in my demo over here I really just have 7 entities, these are not enough to be split over multiple threads. They all fall into the same chunk, meaning they all run this same job on just this one worker thread. It does not matter how intensive the job is, it is all based on the number of entities. If I instead just make a ton of entities, so let me just duplicate this a mountain of times. Okay, so I duplicated the prefab a ton of times, so now I have a total of 1500 entities. And now if we run the same code again, and now if we go ahead and we look, and if now it is correctly indeed using all of the nice worker threads. So that means that this method really isn't suitable for doing super heavy work on just a small number of entities. If you have that specific use case, then instead of using IJobEntity, instead use the one that I mentioned, so the IJobParallel4, and basically handle splitting the logic yourself. So just be aware of this one confused me by quite a bit. But yep, if you do this and you have a certain number of entities, this does work. You just call schedule in parallel and it automatically runs it across multiple worker threads. So in here with this many entities, with 1500 entities, running the code which has this intentionally wasteful thing. With all of that, in total, it is taking 1500 milliseconds per frame, but we are still getting a handful of frames per second because when the whole thing is combined, because of using all of these threads at the same time, the whole thing takes just 100 milliseconds. So this is how you make code multi-threaded. And again, the best results come from combining both multithreading, the job system, with burst. So on the job definition, let's add the burst compile attribute. We only need to add it up here. There's no need to add it for the execute function itself. So like this, if we test, and again, notice that difference. Again, burst is way too smart. And right now I can't even find it. I need to zoom in like crazy in order to be able to find anything. So here it is, I finally found it. So previously it was taking 1500 milliseconds and now it is taking just 0.01. By the way, quick tip to check if it's using burst or not. Look at the color over here on the profiler. If it's in green, then it is indeed using burst. Again, I'm assuming burst is way too smart and it's intentionally identifying that this code is just wasteful, this is nonsensical. So I'm assuming it is actually identifying this and just deleting this useless code. But still, even in regular scenarios, in proper scenarios without this kind of testing code, even in that, burst is an insanely good thing. It is a really excellent way to get extra free performance by just following some good data-oriented design. So when you combine the job system along with burst, you can get some really insane results. Now let's learn about tag components. This is a really easy and extremely powerful tool. Basically, it's how you can add a tag to an object to mark it as some sort of type, like for example the difference between a player and an enemy. Thankfully, tag components are insanely simple. First, let's actually see the problem that they solve. So right now we have these rotating cubes. Now let's say I want to also have a player object. So let's go ahead and make a player. So inside my entity subscene, I'm going to create a new game object. This time for player, let's say it's a capsule. Let's move it a little bit. I'm gonna give it a different color. And inside I'm also going to add a simple cube just to be able to see where this transform is facing. Okay, so that's my basic player. And now let's say that the player will also rotate, so let's also add the usual rotate speed component. However, we want the player to rotate based on input and not constantly like all the other objects. Whereas right now, if we hit on play, and nope, this is not what we want, the player is rotating alongside all of the other cubes. Basically what we want is for this rotating cube system, for this one to only apply to the cubes and not the player. Meaning that we need some kind of way to identify exactly what is a cube and what is a player, so that's where tags come in. Like I said, they are extremely simple. We just make a new component as usual. So let's create a new C# script, call it the player authoring, because again, we're going to place both the component and the authoring directly inside the same script. Let's go ahead and attach a player authoring to the same player component, and let's open. And over here, for our authoring component, which is going to be our mono behavior, for this one, we do not have any fields. We have an empty authoring component. Then let's make a regular component, an ECS component. So a public, this is going to be a struct. Let's just call it player, and this one is an I component data, which again exists inside unity.entities. Now this one also has no fields at all. This is a tag component, which is really just an empty component. And then let's make our baker. So inside our authoring class, let's make our usual public class baker. We implement baker of type player authoring. And on our bake class, on this one, we're basically just going to add the component. So again, let's first of all grab the entity, get entity. And for this player, the player is going to move, so let's use dynamic. Then let's call add component, pass in this entity, and just do a new player for the new player component. So that's it, no fields, no data, nothing. Over here, inspecting our player, if we go into the entities inspector, on this one, if we look up top, we can see a section just for the tags, and if over here, we do see our player tag. Okay, so this one is correctly tagged as our player. And over here in our rotating cube system, let's go down to our job where we are rotating the cubes. And right now, this job will run on every single entity that has both a rotate speed component and a local transform component. This includes the player, so in order to not include the player, we can add a nice attribute to the job that is going to be the one called with none, and then basically we add any types that we don't want this job to run on. So in this case, let's go type of our player component. Basically now with this component, this job will run on every single entity that has both a local transform and a rotate speed component, but no player component. So it should run on everything except the player. Let's test. And yep, it does work. All of the cubes are still rotating, but the player is not rotating. Okay, great. By the way, here we saw by using this attribute in order to make this job not run on entities that have the player component. But over here, the other method, the for each, we can also do the same thing. The way we do it inside of this one is we've got our system query. And then after the query, so after the parentheses, we can then add pretty much the same thing with none. And then we pass in the type of type player. And yep, just like this, now this for each will only run on all entities that have rotate speed, local transform, but no player. And also yet another alternative is obviously we could do the opposite. So instead of tagging the player and then writing this with none, instead of that, we can actually tag the cubes. So let's make our rotating cube tag. So as usual, C# script for the rotating cube authoring. And over here, the mono behavior, this one is empty. Then we've got a public struct for our rotating cube. This one is going to be IComponentData, and inside this one is empty. Then on this one, we've got our usual Baker class, and then we simply have to implement our method, and over here get the entity and add the component. Yep, just like this. And now on the rotating cubes, a while ago I made them a prefab just so we could easily modify all of them. So let's go inside the prefab and let's add the rotating cube authoring. And yep, this one should now tag it as a rotating cube. And now in our system, either over here on the for each, instead of saying with none, we can say with all. So with all or with any, in this case, either one will work. So with all of the rotating cube. So this works, this one will now only run on the cubes. And same thing over here, we can use the attribute. Let's go with all. And same thing, the rotating cube. So now this job and this for each, both of them will run on things that have the rotate speed, the local transform, and the rotating cube component. And also, just for completeness sake, of course, the other alternative that you have is instead of using the with all, we could just use a ref RO over here of our rotating cube. That would also work, but that would be quite a bit wasteful since we don't really need to access that tag component. We really just want to run the query that has that tag. So when working with tags, do not include them as a ref RO, instead use the with all, either the function over here or the attribute on this one. And if we try running this code, yep, exactly the same result. So now that rotating logic, that one is only being applied to entities that have the rotating cube tag. So that's how simple tag components are. They're literally just empty components, which are really great for identifying your objects as being of a specific type. So things like the player, enemy, bullet, money, and so on. Whenever you want to identify anything as something, make sure you use a tag component. Next, let's learn about aspects. However, before we do, let's actually first see the problem that they are meant to solve. So for that, let's make another simple component in the system to move our cubes. Let's go ahead and make a new C# script. First for the component, so movement authoring. Let's go ahead and add this one to our rotating cube. So let's just add the movement authoring and let's open it. And over here, let's actually do something fun. So let's do so that the authoring component, this one is completely empty. But then we are going to have a movement vector in our actual component. So let's do a struct for our movement. So IComponentData. And on this one, we do have something. We do have a float3, which by the way, a float3 is really pretty much exactly the same thing as a vector3. This one just exists inside the Unity mathematics library, and this one is optimized to be used with dots and bursts. But in terms of logic, it's literally the exact same thing as a vector3, meaning if we go inside it, we can see this one has an X, Y, and Z components. So we've got a float3, and let's call it the movement vector. So we have some data in our component, but we have no data in our authoring component. Now let's go ahead and make our usual Baker class. On this one, let's get our entity, and then on add component, let's add a component onto this entity, and the component will be our movement component, except now we don't have this field to grab directly from our authoring component. I didn't do that just to show you how you don't have to. You can make some authoring components that do some kind of processing in order to actually generate the final component data. So over here, for example, let's just set it to a random value. So we can just set movement vector equals a new float3. Like I said, this is the same as a vector3, so we've got an X, Y, and Z. We just need to set these up. So let's just put a random vector, which by the way, the mathematics library also has a random, but for simplicity's sake, I really enjoy using just the simple Unity Engine one. So let's go inside Unity Engine to use that random specifically. Okay, great, just like this. So when we attach this authoring component to an entity, it is going to bake that entity and pass in a movement vector with a random movement vector. Now that we have this, let's make a system that will both move and rotate our cubes. We want to do both of them. So let's go ahead, create a new C# script. Let's call this the handle cubes system. And over here for this one, let's go ahead and make it an ISystem. Then as always, we need to make this a partial struct. Okay, let's write our onUpdate method. And on this one, let's keep it simple, and instead of using a job, let's just use the regular for each method. Which actually, this is probably what you should do when you first make a system, meaning first use the simpler for each method that works just on the main thread, get it working like that, and then convert it into a proper job if you need to. So over here, let's do a for each. Let's write the query first, so systemapi.query. In order to both move and rotate, we are going to need the local transform component, and we're going to need this one as a ref RW because we are going to actually move. Then in order to know how fast to rotate, we are going to need the rotate speed component. That one is just for reading, so ref RO for the rotate speed component. Next, we are going to need to know how fast to move and where to move to. So we need the move speed component, again, just for reading, for the movement component. And finally, we don't want this to run on the player, so let's also call with all and pass in the type of our rotating cubes. Alright, so this is our query. So inside our for each, we just need to use all of these. So let me just write all of this. Okay, so we have our query with all of our components. Then we do the logic, so just rotating and moving, all of it pretty simple. Just go into the local transform. Go inside, first of all, the value RO in order to rotate it. So rotate it on the Y, and let's do the same thing. Grab the rotate speed, grab the value RO, and grab the actual value. Multiply it by our time.delta time inside the system API. So the time.delta time. This one is going to rotate, but it doesn't actually modify the value. So let's go inside the value RW and set it to this one. This one rotates, then we just need to move. And for moving, we're going to do the same thing. So local transform, go inside the value RO. In this case, it's the translate. Then we need our movement vector, so movement.valueRO, and grab the movement vector. And again, make it frame rate independent, so system API.time.delta time. Okay, so that's it, some pretty simple logic. This is going to both rotate and move the component. Let's also just go ahead and disable our rotating cube system. We can either delete the script, or just over here on the update, we can just go into the state, so that's the system state variable, and just set enabled equals false, and let's return so it never runs once. This will basically disable the system from running. So with this, let's test. And if everything works, the cubes are both rotating and moving. Okay, great. So everything is working. But looking over here at this query, it is becoming quite massive with so many components. So this is exactly where aspects come in. An aspect basically groups multiple components into a single logical unit. In order to define an aspect, first we need to define a script. So let's create a brand new C# script. Let's call it the rotating moving cube aspect. And then inside of this one, for this one, we are going to implement IAspect, which exists inside using unity.entities. Now, this interface has no methods that we actually need to implement. It's basically just a tag to mark this script as an aspect. Then an aspect is not a class, instead it is a struct. And again, this one also needs partial for the source generation to work. And one more thing specific to aspects is these need to be marked as read-only. Okay, great. So now here we can add fields for all of the components that make this aspect, that make a rotating moving cube. And to add a component, let's do the usual. So let's make them public. Then over here we use either refrw or refro. And let's begin with the local transform that we do want to write. So let's go refrw for the local transform. Call it the local transform. Next, we also need the rotate speed. So for that one, refro of the rotate speed. And finally, we got another one for the movement. And as you can see, since aspects need to be marked as read-only, all of these fields also need to be marked as read-only. So read-only on all of these. Basically, this is the C# read-only tag. Basically, it makes sure that we can never modify this field directly. So after being set, we cannot modify it. It looks a little bit confusing to have something as marked as both read-only and then refrw for read-write. So it looks a little bit strange, but yep, this is exactly how you write it. Use the C# read-only keyword and then refrw or refro. Okay, so we have all of the components that we need in order to make this aspect work. And then we also need to include the cube tag. Now, suddenly the with_all attribute does not work here. So adding the with_all, just like we saw previously, this one suddenly does not work on aspects. Instead, right now, in order to add some kind of tag component, is we can add it over here as a refro. So we can do a read only, make it a refro. In this case, we need the rotating cube tag component. So this does work. However, it's a bit wasteful since we never actually need to touch this component. So it would be nice if the with_all attribute worked here. Although there is an alternative that I will mention in a little bit. So right now we do have all of the components that make up our rotating cube aspect. Basically, we have the exact same components that we had over here on our system. And now that we have defined the aspect, now we can simplify this huge query with just a single aspect type. So over here, instead of all of these refro, instead of all of this movement and so on, we can just use the rotating moving cube aspect. And over here, same thing. Now we just need one of them. So the rotating moving cube aspect, just like this. And yep, that's it. So as you can see, this really simplifies that query. Now we just have one aspect instead of tons and tons of components. Also note how over here we do not need to add the refro or refrw. Basically, the aspect itself, this works as a pointer and will already have the access that you define over here in the aspect definition. Now for the tag alternative that I mentioned, like I said, adding it here is a little bit wasteful since we never actually need to touch this data. So if you need absolute maximum performance, just remove it over here from the aspect and set it over here on the system, use the same thing that we already saw. So just add with_all and then we can include our rotating cube tag component. Yep, just like this. So this way it is technically slightly more efficient, although in terms of readability, I think I prefer putting it on the aspect itself. So I think this one is a little bit easier to read. The best way would simply be if they allowed using the with_all component, the with_all attribute over here directly inside the aspect. That would be great, so maybe they will add that in a future update. Okay, so here we have our query with just our aspect, and then over here for the logic, now we can access the aspect components and make our changes. So go inside the aspect, then let's say go inside the local transform, then go inside the value RW and so on. So you could do this would work just fine. But another great bonus of aspects is that you can add logic directly inside of them. So over here in our aspect, let's just make a function. So a public void move and rotate. And over here, let's really just copy this code. So let's copy this, put it in here. And the only thing that we don't have direct access is to the delta time from the system API. So let's just receive it as a simple parameter. Okay, yep, just like this. And over here in our system, let's just go inside our aspect and simply call our function to move and rotate and pass in the system API time.deltaTime. And yep, that's it, just like this. Let's test. And yep, everything still works. So here you can really see how this code is now much simpler than it was before thanks to using our aspect. That is really the power of aspects, is allowing you to group several components together into one logical unit. Next, let's learn about something that is crucial to making pretty much any game, prefabs. And thankfully prefabs in ECS are also really simple. Right now we manually populated all of these cubes in our world, and now instead of doing that, let's make them spawn at runtime. So let's make a system that will spawn them. And before we do that, first we need to find some way to store a reference to our prefab. So let's first make a component to store that, and then our system will use that component. So let's go ahead, create a new C# script for the spawn cubes config authoring. Basically, this is going to be the config file containing all of the config data for our spawn cube system. And over here in our mono behavior, let's add a regular game object field for our cube prefab. So public game object for the cube prefab. And then we're going to want to spawn multiple of them. So let's also add an int for the amount to spawn. Okay, great, like this. Then here in the editor, let's make an empty game object inside our entity subscene. So let's create it. Name it spawn cubes config. On the regular inspector, let's go ahead and attach our authoring component. And for the prefab, let's drag our rotating cube prefab. And for the amount to spawn, let's go with 5. Okay, so that's our authoring component. Now we need to convert this into an actual entity component. So for that, let's go ahead and make our entity component. So again, let's follow the exact same thing. So let's make it a struct for spawn cubes config. And this one is iComponent data. However, on this one, instead of making another field of type game object, instead of that, we're going to make it of type entity. So public entity, and let's call it cube prefab entity. So you have this, and then for the end, the same thing. So the amount to spawn. Okay, great. So all we really need to do is convert our regular game object prefab into an entity prefab. And we're going to do that on our baker. So let's make our usual baker class. We're going to do baker and extend the spawn cubes config authoring. Then over here, as usual, let's pass in add component. So that means we need our entity for this entity. So let's go ahead, get entity. And in this case, actually, since we're using this config component, this is really just a data component. We don't really want it to exist anywhere. So for this one, now we can use none in order to make it just a little bit optimized, since we don't really need that transform component. Then let's add a component onto this entity and the component new spawn cubes config. And now inside here for the data, for the amount to spawn, let's just go into our authoring and grab the amount to spawn. And then for the cube prefab entity, the way we convert our game object prefab into an actual entity, thankfully that is extremely simple. We'll literally just use the same getEntity function. So get entity. And this one has a version that takes in a game object. So we can just go inside the authoring component and let's grab the regular game object cube prefab and then usage flags, same thing, let's go with dynamic. So yep, that's it, really simple. We just call getEntity and this is going to automatically convert our game object into an entity prefab. So with this is going to work. We're going to have our nice config component. We can even test it out over here. Let's go ahead and run our game, then look into the entity inspector. And yep, there it is, the spawn cubes config. And yep, we do have our rotating cube prefab entity. Also note how on this one, we do not have any transform components. Again, that is that little optimization thing. If we look into the other components, the other entities, all of these do have local to R, local transform, and so on. But on this one, which was optimized, this one does not have any transform data. Okay, so great, here we have our cube prefab entity. Now let's simply just instantiate it. So let's make our system to handle that. Let's go ahead, create a new C# script. Let's call it the spawn cubes system. And then over here, we can either make this a SystemBase or an ISystem. Let's go ahead and do a SystemBase just to be different from what we've already seen. But like I said, either one works. So a SystemBase, just need to mark this as partial. And then we need to implement our abstract class. So we need to implement at least the onUpdate method. But then, like I said a while ago, you should also implement the onCreate if you have any requirements. So over here, let's also implement override void the onCreate. And on this one, let's call require for update, which by the way, this is a little bit different from the one that we saw on the system. So if we go inside the rotating cube system, on this one, on the onCreate, when working with an ISystem, we've got a system state over here on the parameter, and we go through that and call require for update. Whereas over here on the system base, we can just call require for update and then pass in the component that we need. So in this case, it's the spawn cubes config, just like this. Okay, so yep, with this, now the update will only run when there's an entity with the spawn cubes config. That's good because we're going to actually need that object to exist in order to run some logic here. And now on this logic, we really only want to spawn the cubes once, so let's just disable this system right after the first update. The way we do that on a system base is just do this.enabled equals false. That will make sure that this update is only going to run once. And over here, in order to get our spawn cubes config, for that we can use a super useful function from the system API. We just go inside system API and we call get singleton. This one, like the name implies, gets a singleton. So we just pass in the type, so the spawn cubes config, and this one is going to return our spawn cubes config. Now importantly, this get singleton function, this one has a whole bunch of really useful safety checks. If you have 0 entities with this component, then it's going to fire an error. So again, really important that we add the require for update before this update runs. And if you have more than 1, meaning it's not really a singleton, if so, then also fires an error. So basically, in order to call this get singleton function, in order to do this, then this must actually be a singleton, meaning there has to be one and only one entity with this component. These are some really great safety checks because they really enforce you to actually implement the proper singleton pattern. So with this, we can now easily access the data inside of this component. So let's just do a basic cycle through the amount to spawn. So just say basic for starting on 0, going until the spawn cubes config, the amount to spawn, I++, okay. And now here, let's simply spawn. And the way that we spawn a brand new entity prefab is really simple. We just need to access the spawn cubes config, and inside we've got the cube prefab entity. And the way we spawn it is we just go inside the entity manager. Inside this one, we call instantiate, so just like you would instantiate a regular game object. And this one takes a parameter for the source entity, which is indeed our cube prefab entity, just like this. All this is doing is really just copying the source entity. Since entities are really just data, instantiating simply means copying all the data in memory. The only special thing that instantiate does is how prefab entities, they've got a prefab tag component. This is a special tag component that all of the entity queries ignore, since normally we don't want to run any logic on the prefabs themselves. So when calling instantiate, it copies all the data from that prefab, copies everything except that one prefab component. And yep, that's it. Super simple. So this will return our spawn entity. And then if we want, we can initialize it. So we can go inside the entity manager and call set component data. And we can set any component to any data that we want. But at the same time, our prefab, this one already has a bunch of authoring components. These are still going to run when this is converted into an entity. So we don't need to manually initialize all of these authoring components. So for all of this custom data, we don't need to do anything else other than just spawn it. Although actually one really interesting thing is that the bake happens just once for the prefab, meaning all of these authoring components, they will be converted into the corresponding entity components just once. So for example, in this scenario, we have our movement authoring component. And for this one, we defined over here on the baker, it generates a random movement vector. But like I said, this bake will only happen once for the prefab itself, will not happen every single time that we instantiate a new entity from that prefab. So in this case, all of our spawned objects, they will all have the exact same movement vector, since again, this bake only runs once. So just something to be aware of. The bake only runs once when the prefab is converted and not every time that you spawn an entity from that prefab. So over here for set component, we don't need to bother with all those custom components. Let's just put it in a random position. So the set component data, this one takes an entity. So let's go inside our spawn entity. And for the component data, in order to put it on a random position, let's just modify the local transform. This one takes a certain position. And the position is a float3. So let's go ahead. Let's implement using unity.mathematics. And we're going to have our nice float3. Again, same thing as a vector3, so x, y, z. So this is going to spawn it on some random position. Although actually, here's another thing that confused me quite a little bit when I first was researching this topic. I initially just did this in order to spawn all of the entities. And actually, if we test this, it does work. It will spawn the entities and it will position them on a random position. So here, let's quickly test. And before we do, let's actually get rid of the rotating cubes. So we just want to spawn them. So let's test. And look at that, nothing is actually visible. However, if we look in the entities hierarchy, yep, all the cubes are indeed being spawned. So again, this is the thing that confused me a little bit. And the reason has to do with the defaults. And we can look over here on the local transform and see, yep, the position is indeed being set correctly. But over here, the scale is a float, and the float by default is going to come out to 0. So that is why we don't see anything. The entities are all actually there, but since they've got a scale of 0, they're not visible. So technically, when spawning a new local transform and setting some data, technically you can just insert the ones that you need, so in this case just the position, but if you do, know that everything else is going to default to 0. So in order for you to not be confused like I am, if you go ahead and modify local transform, just go ahead and also apply the rotation. We can go inside the quaternion, this is the one inside the Unity Mathematics library, and just use identity for the default rotation. And again, let's also put on the scale, just so this one does not default to 0. Also, another option exactly to solve this sort of problem is how the local transform, if we go inside that class, local transform, this one has all sorts of helper functions, similar to the rotate and the translate that we saw a while ago. We can use this to automatically create the local transform with a certain position, rotation, scale, or just position, like for example this one. So we can use this one with our custom position, and then basically this would create a local transform with a certain position and set the scale correctly to 1. So all of the helper functions inside the local transform, all of these can be quite useful. Okay, so just like this if we test. And yep, here we do see a bunch of cubes being spawned, and yep, everything still works, so all of the same rotating and movement logic, all of that is still working the same as previously. We can easily go inside our spawning cubes component in order to spawn more or fewer cubes. And yep, there you go, everything spawns and they all move. Alright, awesome. Now I should note that there are more efficient methods for spawning entities if that's really the only thing that you want to do and if you want to spawn a ton of them. If so, then instead of instantiating them like this, just literally one by one, instead of that, you can use the other functions over here for the instantiate. So we've got this one that just takes an entity and spawns another entity. Or alternatively, we have, for example, this one. This one takes a source entity and then creates a number of entities that are all placed inside a native array. So basically, you construct a new native array with a certain size, and then this one will instantiate entities to fill that entire array. So if you spawn an array with 100 elements, it is going to spawn 100 entities. Then you would simply cycle through that entire native array and set the component data on all of those entities. So just be aware, if you want to spawn tons of things, it might be better off to spawn all of them at once instead of one by one individually. Also, speaking of maximum performance, so over here this code works, but for maximum performance, instead of using over here entity-manager.setComponentData, instead of this one, you can use SystemAPI.setComponent. And yep, this will do the exact same thing, but this one has some nice performance benefits. So in general, whenever possible for maximum performance, you should prefer using the functions inside the system API, since a lot of those will have some nice performance benefits as opposed to using the entity manager directly. But on a simple system like this one, either one works. And also another very important thing on spawning entities. Over here, note how we are spawning them directly through the entity manager. So that's perfectly fine here. Like I said, technically this is not the most performant matter, but over here we're only running this update once, so really over here we have no concerns when it comes to performance. And we're also not cycling through anything, so again, also not an issue. But for example, let's say that our player is firing bullets. So let me just quickly make a system for the player to manually spawn some bullets. Let's go ahead and just create a new C# script called the player shooting system. And then over here, let's make this one a system base. So system base inside using unity.entities. Let's make it partial. Let's go ahead and implement both these. So both the onUpdate, and let's also do override void the onCreate. And on the onCreate, let's call require for update and make sure this one only runs when the player tag component actually exists. Okay, so we have this one, and then on update, let's go ahead and fire some bullets. And for firing bullets, let's actually simply spawn a cube. So let's consider a cube to be a bullet. So let me just copy this. In order to fire it manually, let's just check if the player is holding down the space. So over here, I'm just doing some basic testing code, so just get key down. So let's test for the space key. So if the player is not pressing space, if not, then let's just return. And if the player is pressing space, then we're going to run this code. Then for the bullets, instead of going through this amount to spawn, instead of that, let's cycle through all of our players. So let's do a for each system API. Let's first handle the query. We're going to need to know the player's position in order to know where to spawn the bullets. So let's use a refro because we only need to read it for the local transform. So this is the only one that we're going to have. So we just need the local transform in the query. And let's also make sure this one only runs on the player. So with all of the player tag component. So we cycle through all the players, we get the local transform. Then over here, we are going to spawn the cube. So that is going to act kind of like a bullet. And then for spawning it, let's simply spawn it directly on the player's position. So over here, let's just go inside the local transform, grab the value RO, and let's just grab the same position. Okay, so just a super simple system. So when we are pressing space, we are going to run this logic. We get the singleton in order to get our prefab reference, and we're simply going to spawn a cube directly on top of the player. So let's see. So here we have the player, and if I press on space, and if there you go, it does indeed spawn a cube directly on top of the player. Okay, great. So again, we still have the exact same logic that we had previously, just spawning it directly. So over here, we're still using the entity-manager.instantiate. However, one very important thing about dots is that spawning or destroying entities, that is what is known as a structural change. Basically, the backend of dots, that one is storing a ton of tightly packed arrays for all of the entities and all the components. That's really how this system is so insanely performant. But of course, if you spawn a new entity, you are going to modify those underlying arrays. So while cycling through some arrays, while cycling through some entities, while doing this, you really don't want to modify it. So in order to spawn or destroy entities while in a job or in a for each, in this case, you should actually use what is called an entity command buffer. Now I should also obviously say that this code actually works. This is not a problem. As we saw, it is running perfectly. But the reason why it works is because the new prefab entity does not match this query at all. We're spawning bullets, not players, so the new spawn entity will not have a player component, so it does not match this query. However, if the instantiated entity archetype, if that one did match this query, then it would break this code. So when that happens, for that, like I said, you should spawn entities using an entity command buffer. So let's see how that's done. First, we need to create a new entity command buffer. So let's do new entity command buffer. This one requires a certain allocator. And over here, there are a whole bunch of options depending on how long you want this entity command buffer to live. Now, in this case, we really just want to create it in order to spawn our entities, and then we want it to be disposed of. So let's use the simplest one, the temp allocation. This one is going to be created temporarily, and then automatically it's going to be disposed of. So we don't need to manually dispose it ourselves. We do this in order to create a new entity command buffer. But of course, we don't actually want to create it for every single player. We just want to create one and then spawn all kinds of entities. So we do this outside of the for, okay? Then we go inside the for and for each enemy. And for each player, we want to spawn our bullets. So over here, we go inside this one and we just call the same instantiate function. This one, as you can see, also has all kinds of options. We can spawn just one or multiple. So for now, let's just spawn one. So let's literally just replace this exact same code with this one. Everything else is exactly the same. However, importantly, this isn't actually instantiating the entity over here. Over here, we are simply adding that command to a command list that will be executed later. So we do that in order to record an instantiate command, and then same thing over here for the set component data, except over here, for some reason, instead of being called set component data, it is only called set component. I'm not sure why this function is different, but it just has a different name and everything else works the same. So again, this is also going to just register a command. It is not actually going to set any component data just yet. So we do this, and basically over here, we are queuing up all kinds of commands. And then after our for, after our cycle, so basically after we are far away from those issues that I mentioned with all of those tightly packed arrays, after this, in order to actually execute those commands, we can go here and call playback. And this one takes an entity manager that is actually going to spawn the entity, so let's just pass in the reference to our entity manager. And yep, just like this. So basically by doing it like this, we have no structural changes over here directly inside the for each. We are just recording some commands, and we are only executing those commands after we exit the cycle. And if we run the code, everything is still going to work exactly the same. So if I press space, yep, there you go, it is spawning cubes, everything works great. So for spawning things, usually you have these two options. You can use an entity command buffer, or you can simply use the entity manager instantiate. And another note on getting maximum performance. So here this works. It is going to allocate the entity command buffer and then dispose of it. But in order to get a tiny bit more performance, instead of using a temp allocator, instead of that, you should use the world update allocator. This is a special allocator that exists by default. It lasts for 1 to 2 frames and is automatically disposed of and has some nice performance benefits. Now, speaking of structural changes, one change is spawning or destroying entities. So over here we are instantiating. This is a structural change. Then yet another type of structural change is simply adding or removing components to an entity. So if over here I go into the entity manager and I call add component, this is going to be a structural change. Basically, it has to do once again with how dots works in the background. How the whole thing is based on entity archetypes, which are specific groups of components. So by adding or removing components, you are basically creating a brand new archetype, so things need to be moved around in memory. So ideally, you should avoid adding or removing components as much as possible. If you need to do something like that, like for example, let's say you need to define if the player is in some kind of stunned state. If so, then instead of adding or removing some kind of stunned component, instead of that, you can use what are called Enableable Components, which let you enable or disable without triggering a structural change. So let's see exactly how that's done. So first we build a component as usual. So a new C# script, let's call it stun authoring. And over here for the authoring component, let's leave it just like this, just empty. And then let's make the actual entity component. So let's go ahead, call it just stunned. And for this one, let's implement iComponentData as usual, but then also iEnableable Component. Then if you want, this can have any fields for any data that you want, or it can simply be a simple tag component. And then up here in our authoring component, let's implement our Baker class. And in this one, let's do the same thing. So entity, let's call get entity. And for this one, this is on the player. So sure, let's pass in as dynamic. Then let's add component onto this entity. Let's add a new stun component. So just like this. And then we can call the function setComponentEnabled. And we're going to modify the one of type stunned. And then we can set it to either enabled or disabled. First, let's pass in the entity. And then let's say we don't want the player to start off stunned, so let's say false. Okay, so that's it, super simple. So we basically just implement the Enableable component, and then when adding that component, we can optionally set it as enabled or disabled. Then over here in our game, let's go ahead and just add the stun authoring component. And then for example, over here on the player shooting system, on this one, we are cycling through all the players in order to spawn all the bullets. So we are calling with all to see all the players. And in this case, we only want to run this query if the player is not stunned. So for that, we can add the with disabled. So this query will only work if a certain enableable component is actually disabled. So let's go with our stun, just like this. So this query, this for each, will only run on entities that have a local transform component, also a player tag, and also a stun component that is set to disabled. And then just for testing, let's put up here just some simple testing code just to swap the stun state. So let's test input, get key down for some testing keys. Let's go with the T key. In this case, for some testing, we know that we only have one player. So again, just for some simple testing code, let's go inside the system API to get the singleton entity of type player. And then we can go with the entity manager and call setComponentEnabled of the stun component on this player entity. And when we press T, let's set it to yes, let's set it to stunned. And on another key, so let's say on a Y, let's set it to not stunned. Okay, just like this, let's see. All right, so here we are, and we can actually look at the player. So we can select the player and go inside the entity inspector. And over here, yep, we do see up here on the tags, we do see there's a stun tag. And right now, if I press on space, yep, there you go, it is spawning a bullet. However, now I press on T, and yep, note how that one became checked. And now if I press on space again, and nope, it is not spawning anything, because again, it is only running that query if the player is not stunned. So press on Y, that one becomes unstunned, and space, and there you go, it still works, so stun, unstun, everything works. Alright, great! Now, like I said, the main benefit is this is not a structural change, which makes enabling or disabling these enableable components makes it super fast. So instead of adding or removing this component, instead of that, we just either enable or disable it. Okay, so now let's cover one of the most important things about ECS, which is how to interact with it from game objects. This is very important because it is the recommended method for working with dots. There are many things for which game objects are still excellent, so the recommended workflow is mixing both dots and game objects rather than going 100% with either of them. So over here I previously prepared this simple game object. It's a simple shoot pop-up, so inside I really just have some text just saying shoot, and then I've got this simple script. So over here, really on update, it just moves this component upwards, and after a certain amount of time just destroys itself. Again, super simple. Note how this is a regular script. Absolutely nothing over here on this pop-up. Absolutely nothing has to do with either entities or dots. This is a regular game object, regular monobehavior component. The game object itself, again, like I said, regular game object, absolutely nothing to do with any entities. What we want is basically spawn this regular game object whenever the player entity spawns a new entity bullet. So let's make some kind of script to handle that. Let's go ahead, create a regular monobehavior, regular C# script, call it the player shoot manager. Now let's make a regular game object to run the script. And again, importantly, we want a perfectly regular game object, so we do not want to create anything inside the entity subscene. Nope, just out here, and let's create an empty regular game object. Let's go ahead, give it the same name, and reset the transform, and let's attach our component. Okay, just like this. And on this script, basically we want to know when the player is actually shooting, and when they do, then we want to spawn our prefab. So over here we have our player shooting system where we are actually spawning our bullets. And now a while ago, I made this a system base. And like I said, the difference between SystemBase and ISystem is that SystemBase is meant for managed components and ISystem is meant for unmanaged. And one of the easiest ways for us to connect both game objects and the entity systems, one of the easiest ways is simply by using an event. So over here, since we are in SystemBase, we can use managed components. So let's use a regular managed event handler for handling some regular C# events. So just super simple, public event handler. Again, super simple event. Let's call it onShoot. Event handler is a type of a delegate, which is a managed type. Now, if you don't know about events, I covered them in detail in a previous video. Same thing for delegates. Okay, so basically with this, we have our normal event. And then down here, when we shoot, let's simply fire off the event. So again, really simple, just do the exact same thing that we're used to using. So just event, let's invoke it with the usual standard this event args.empty. Also, by the way, one more quick tip. Over here when doing systemapi.query, for this one, just in case we need to know the entity, like for example over here on the event, it might be useful to know which player is actually shooting a bullet. For this one of the many options that we can add over here onto the query, one of the many options is with entity access. And if we do, then our entity over here, the tuple that this returns, this one is going to have a reference to an entity right over here at the end. So for example, in this case, we can do this in order to, over here when we shoot the event, we can pass in the entity reference as who is actually shooting this bullet. Okay, so just like this, pretty simple, we've got a regular shooting event. And then on our regular game object script, let's just clean this up. On this one, we really just need to hook onto that event. And for that, that means that we do need to find some reference to this player shooting system. And thankfully, that's pretty easy since there is only ever one system in the world, which means the systems are always singleton, so that makes it really easy to find. We can just go over here on the player shoot manager. Let's do a private void start in order to hook onto our event. However, over here, we can't access the system API. This one does not work. This one only works on systems. As we can see, you may not use a system API member outside of a system. So instead of this, the way that we find that is we first need to access the world, and we can access the default world by going into world.defaultGameObjectInjectionWorld. And over here, we can get an existing system. And in this case, since we are using a system base, we need to use the managed version. So for this one, for the player shooting system. And now that we have this one, we can go and do the same thing. So just listen to the event. So just some usual code, nothing to do with any entities. The only entity thing is over here converting the sender into an entity. So an entity for the player entity. And let's go ahead, grab the sender, and we need to convert this as an entity. So let's go ahead and cast it down into an entity. So we have this, and now in order to know where to spawn our prefab, for that we need to know the position of this player entity, which means we need to access this player entity, the local transform. So for that, let's go inside the world, default game object injection world. Let's grab the entity manager, and from that one, we can grab the get component data. We want the local transform component, and the entity that is going to be our player entity. So this is going to return our local transform component. Then when we have this one, we've got the position. So this contains the position of the player. So now let's just do a regular game object instantiate. So instantiate, and we just need the reference up here. So let's go up here and add it as a regular field. So serialized field, private game object for the shoot pop-up prefab. So again, a regular game object component. And then over here, let's go ahead. Let's put it on this position with no rotation, so quaternion identity. And by the way, note how even though the position, this one is a float 3, it automatically gets converted into a vector 3. Okay, so that's it, super simple. So we basically just go through the default world in order to get the instance of our shooting system. And then from that one, we hook onto the event, just a regular event. And then we grab some data from that entity and spawn our regular game object. Let's test. So just over here on the player shoot manager, let's just make sure to add the shoot pop-up and let's test. So here we are, and if I press on space, and yep, there you go, there it is, the shoot pop-up, it does work, it does spawn the player, and yep, everything works great. Alright, awesome. Again, note how this pop-up, this is a completely normal game object element. The player itself is an entity, and it is being controlled by an entity system, but this game object, this is an entirely game object. The pop-up has absolutely nothing directly related to any entities. We've got an entity over here, then a game object over here, and we simply have a script, just a regular manager, just a regular monobehavior component, and this one is handling the connection between one and the other. So as you can see, this is one way for how you can connect a game object onto an entity. You can have some kind of entity system that fires off some kind of event, and then have some kind of script that listens to that event and does whatever it wants, like for example, spawning a game object. This works. So basically over here, we have the monobehavior side grabbing some data directly from the entity side. However, alternatively, we could also do the opposite. We could have our system in order to call some kind of function directly on the monobehavior. So for that, the super simple way is pretty much exactly the same thing that we did. So we grab the existing system, which is going to be a singleton. So you can pretty much just convert this regular monobehavior also into a singleton. So let's use the usual singleton pattern that I've used in so many videos. So for the player shoot manager, call it instance, make it with a public get and a private set. Then let's do a private void awake, and on awake, let's set the instance equals this. Okay, so we have our nice static instance. And now instead of having these events, instead of having this monobehavior go grab data from the other side, instead of that, let's go ahead and make another function. So let's make a public function. Let's call it player shoot, and let's receive vector 3 for the player position. Then over here, we just do literally the same thing. So we call instantiate, shoot that one onto this player position, just like this. And over here on the player shooting system, let's go down to where we are doing all of this. And now we can just go the player shoot manager, access the instance, and call the player shoot function. All right, yep, just like this. Let's test. So here we are, press on space, and yep, everything still works exactly the same. So as you can see, there are multiple ways to have our game objects and entities interact with one another. You can have the mono behavior side as the ECS side for some data, or the other way, you can have the ECS side like some kind of system, access some kind of mono behavior and tell it to do something. Or yet another option you have is just know there are ways to store managed data directly inside a component. You can use managed components. They do have a whole bunch of limitations, but it is possible. So for example, you could have some kind of managed component that holds a reference directly to some kind of game object, like for example a particle system. So you can do that and have the system directly interact with that managed component and do any kind of function, any kind of data, do anything with that managed component. So basically all of those options work, so there are plenty of ways for you to mix both game objects and entities. Okay, so we already covered a lot of stuff that you need to get started, but Dots is huge, so there's really tons more stuff to learn. Let me quickly just go through some tiny details. Like over here on systems, when doing a query, we already saw a whole bunch of options, but there's a whole bunch more. You can just search for with and see all of them. So with all, this one makes sure that all of the ones, because over here you can actually include more than one type. You can include multiple components. So if you use with all, that one is going to make sure to run this query on all entities that have all of these components. Alternatively, you have the with any. So this one you can pass in a bunch of components and it's going to run on entities that have any of those. Then you also have with none, which is going to run on entities that do not have any of those components. Also, by the way, over here I said with disabled, but if stunned was enabled and you only want to run some logic on players that are stunned, there is no with enabled. Instead, if you want a component that's enabled, that really just counts as a regular component. So you just put it over here with all stunned, and this would only run on things that also have a stun component and it's also enabled. Also, by the way, all of those are also available over here when you use a job. On this one, you can work with the attributes. So again, you can see with all, with any, with disabled, and so on. Then on aspects, for this one, you can also have an entity field. So you can do public, read only, entity, entity. This works, and basically as you do some kind of query against this aspect, it is going to automatically fill in this entity with that entity. Then in your jobs, if you somehow have some kind of native array component, native array or native list or any of these collections, if so, then the job will basically consider this a read-write field, meaning if you have multiple jobs working on the same native array, it is going to run one after the other instead of running them concurrently. If you do know that you are never actually going to write to the same index on multiple jobs, if so, then you can use the attribute read only. That basically says that this native array, this one is only used for reading, so you can run multiple jobs with this field concurrently. Then on systems themselves, you also have a whole bunch of attributes. The main one is the update before, after, or in group. With these, you can basically have some more control over when the systems run. For example, over here, we can look inside the systems window to see all of the various systems and note all of these various system groups. So by using these, like for example, update in group, you can use this in order to define in which group you want to run this system on, or you can use the update or after to update before or after any of these groups, any of these systems. Then for the systems over here on the system base, if we inspect this, if we go to definition, we can see these have a bunch more functions. For example, we already saw we can override the on update, but there's also one called on start running, on stop running, and so on. So for example, this is related to how on various on create, on various of those, we add the require update component, meaning the system will not start running until an entity with that component actually exists. So you can use these two, the on start running and on stop running on the system base. And if you are working in an ISystem, for this one you can do the same thing, and that exists over here on the ISystem start stop. So you can implement this one in order to have the access to the on start and on stop running. Also, speaking of systems, they actually have an entity connected to them. So here, if we look in the entity hierarchy, look at how right now it's actually empty. And if I start running, yep, there you go. Look at all of these entities that were created, all of these for a system. For example, over here, the player shooting system, this is the entity related to that system. This can be really useful to store some data that is directly related onto a system. Technically, you can also store data directly on the system. So over here, you can store some fields. But in keeping with the data-oriented design, you should really store any system data directly on the system entity. In order to access that entity, for example, when you go inside the entity manager, when you do, for example, set component data, on this one there's a version which takes an entity, but then there's also one that takes a system handle. So you do and go through the system state in order to get the system handle, and just like that you can access the underlying entity for this system. Then something I mentioned a while ago are the native arrays. Those exist in the collections package. So you've got native array, you've got all kinds of those, and you also have native list. This one also exists. Like name implies, these are arrays or lists as usual, but they have native memory access, meaning they are extremely fast, they are burst compatible, but you must be very careful to dispose of them. So for example, if I create a native array of type int, I can do this, native array, and then when constructing, I give it some kind of size and some kind of allocator. So let's say 5, and then allocator, we've got all of these. So if you want to persist, you would create it, for example, over here on the system on create, and then you would reuse it. If you're using it in a job, use some kind of temp job. If something that you only need to persist for pretty much just one frame, use temp. Also importantly is if you use temp, then the system will basically automatically dispose of this array by itself. However, if you use the other ones, so for example, if I use the persistent one, if I do this, then this memory won't be allocated forever. So if you were to do this and spawn one of these arrays directly over here inside an onUpdate, then basically you end up with a memory leak. So if you work with native arrays or native lists or anything like that, if you don't use temp, then you need to make sure to call dispose. Then in terms of holding different sizes of data inside an entity, for that you have dynamic buffers. These are basically arrays that you can hold as a component in an entity. Basically, a component usually has a certain number of fields, but with a dynamic buffer, you can have something that increases or shrinks, basically has any size. So that's a bunch more things for you to be aware of and to research. Like I said, dots is a massive thing, but honestly, I think the basics are really not that difficult to learn. So I do hope that this video helped with that and learning the basics. If you just learned those, then you already have access to an extremely powerful tool. And if you want to learn more, then I highly recommend you look at the documentation. It is really detailed and very well written. There's a project on GitHub with a whole ton of samples. It even includes a bunch of walkthrough videos. So if you want to continue learning more about dots, I highly recommend you go through those. Basically, that's what I did for my own research for these past few weeks. If you found this video helpful and you're feeling generous, then consider dropping a super thanks on the video, or simply please hit the subscribe and the like buttons. It's a small thing, but those really do help, so thanks. And like I mentioned in the beginning, I'd love to do a dots course. I'm planning to do it after I finish my C# course. So do let me know in the comments if you would be interested in that, and if so, let me know what genre you'd like to see. Maybe a factory game or an RTS, maybe tower defense, third-person shooter, vampire survivors-like. There's really many things for which dots would be a great tool for, so let me know in the comments. And if you use Unity at all, then check out my Ultimate Unity Overview course. It features over 70 lectures, each covering a different tool or feature of the engine, including many of which you might not know about that might be super useful for whatever project you're currently working on. Okay, so I really hope this video helped you get started with dots. Thank you for watching, and I'll see you next time.